Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, is that robot listening? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is about robot hearing and how bioinspiration and artificial intelligence are helping roboticists to develop robots that don't just hear us, but really listen. Before we get started, I thought I should give you an update on the funding situation for Robot Talk. Regular listeners will remember that at the start of this season, I talked about the uncertain future for Robot Talk, as the current funding for the podcast is due to end next summer. I'd like to say a huge thank you to everyone who's recently signed up as a paid supporter on Patreon, as well as all the long-term supporters, of course. Your contributions really help make the podcast financially sustainable. Thank you. I'm pleased to say that the financial outlook for Robot Talk is now a lot more positive than it was a few months ago. I've had one organisation generously sponsor an episode in Season 6, and I'm having very promising conversations with several other organisations about future sponsorship. So I'm now feeling more confident that Robot Talk will be able to continue into Season 7, and I'll keep you updated on that. But for now, if you enjoy the podcast and want to see it grow and thrive in the future, please consider becoming a paid supporter on Patreon by going to patreon.com/Claire Asher. So, without further ado, let's get on with this week's interview. I recently had a wonderful conversation with Christine Evers from the University of Southampton about helping robots understand the world around them through sound. Today, I'm speaking to Christine Evers, an associate professor at the University of Southampton, working on machine learning approaches for robot sensing. Hi, Christine. Lovely to have you on the podcast.
Hi, Claire. Thank you very much for having me.
So you direct the Centre for Robotics at the University of Southampton. So to get us started, can you tell us a little bit about the research that's currently going on in the centre?
Yeah, of course. So the Centre for Robotics here at the University of Southampton is a hub that brings together roboticists across research groups and schools. So that reaches from electronics to engineering and computer science. Southampton is an ideal place for robotics research because we actually bring together leading experts across the whole spectrum. So that's from electronics and sensing to control theory, AI, and human-robot interaction. And that breadth actually allows us to tackle robotics as a genuinely integrated system rather than as separate pieces. So the unique capability that the centre actually brings within, I guess, the landscape of robotics in the UK is that we aim to bridge the gap between robot control, robot perception, and interaction. So within that context, perception gives robots situational awareness, from sensing through to machine learning. And that awareness actually enables good control, which allows us in turn to turn information into physical action. And based on actions, we can then enable robots to interact in a meaningful manner with people, with their environments, and with other robots. What makes Southampton particularly strong is that we can also combine all of this with expertise in cybersecurity and verification. So we're not just building capable robots, but we aim to build robots that we can trust. And as that, the Center for Robotics actually fits naturally with the major national initiatives that are hosted here in Southampton, like the UKRI Trustworthy Autonomous Systems Hub, but also Responsible AI UK.
Fantastic. Yeah, I mean, it's a really interesting and broad range of research. The point you made about bringing all these different people together, I think quite often roboticists end up being in like different university departments, and like they don't necessarily get to interact with each other that much because they're working kind of different aspects of it. So it's great that you've got this centre really as a hub for all of that.
Yeah, absolutely. And it's wonderful to see people actually collaborating together and to see new ideas emerge across different research areas and research fields.
Yeah, absolutely. So your research specifically is taking inspiration from human hearing to allow robots to better understand the world around them through sound. So, like, what is the current kind of state of the art in terms of robot hearing, and what insights do you think we can take from humans to improve on that?
So fundamentally, machine listening enables robots to make sense of life and sound. So think about very noisy environments, potentially very crowded spaces, where there are lots of events going on simultaneously and changing all of the time. So you have a highly dynamic and very uncertain environment. So think your home environment, where there might be a kettle in the background, a TV, someone talking, and all of a sudden you hear glass shattering. Or think shopping malls, where there's all sorts of sound events happening and things are changing very rapidly. Airports as well as restaurants are other good examples as well. So ultimately, the goal of my research is to deliver efficient, robust, and interpretable auditory models that actually generalize well across different listening tasks. Robot hearing as a sort of area has made really quite a lot of progress over the last few years. But within that, it faces challenges that are very different from robot and computer vision. So sound itself is a very challenging modality to handle. There's interference from different sound sources in the scene. These sound sources actually impinge on the microphone at the same time. So what we record at a single mic is the mixture of all the different sound events within the environment. And disentangling that mixture is a really difficult task because different sound events have different acoustic fingerprints. They have different onset times and endpoints. And even the same sound source might not actually be continuously active. So a lot of sound sources like speech are intermittently active. So they stop and start all of the time at intervals that are very difficult to estimate. And then, of course, on top of that, we also have environmental factors like background noise and reverberation. So there's a lot of ambiguity and a lot of uncertainty that needs to be resolved, which makes machine listening and robot audition in itself a very difficult task. Now, the human brain itself is actually amazingly capable of making sense of these complex acoustic scenes. So fundamentally, I guess our hearing system multitasks very efficiently and very well. And what we've been sort of experiencing over the last couple of years is that with this current AI summer that we're observing, there has been a lot of work that actually builds on deep learning to make machines hear better. That's not just for robotics, but general audio and general machine listening moving beyond robot audition. The sort of challenge that we're facing, though, within robotics is that these models typically rely on very big data sets and architectures, so model architectures that have a big compute footprint. So, of course, that's on one side an environmental concern because we have to train them and that takes a lot of time and a lot of power. But it's also a major issue for robotics because robots are resource constrained and embedded systems. So a robot doesn't typically carry a server-grade hardware, and a robot operates on batteries, which means ultimately it's going to run out of battery. So much of my current work is focusing on embedding actually our knowledge about the human auditory process directly into these architectures of models that are driven by deep learning. And the underlying hypothesis here is that by building the right structure or architecture into the model, we can make these models much more efficient, much more adaptable, and much less dependent on huge data sets. And it also gives us a better understanding of how we need to extend these models when we need to incorporate cues for different listening tasks. So for example, think about we've trained a model for sound event detection and classification, but now we want to embed spatial information and we want to actually provide the robot with a situational awareness. That extension is not necessarily straightforward, but I believe that actually incorporating our understanding of the human auditory process allows us to do that in a much more principled manner.
Amazing, yeah. You kind of mentioned a microphone, and I think the robots that I've encountered that can hear tend to have one microphone, but humans have two ears, and we get a lot of information from that in terms of like where the source of a sound is. Why don't robots have two ears or more?
There are actually robotic systems that have multiple microphones. So there are robots that actually are binaural listeners, so with two ears. And there are robots that have microphone arrays. So an array being multiple microphones in a specific geometry that is embedded in the embodiment of the robot. They are reasonably rare, which actually makes research and machine listening quite tricky because you want to find a system that allows you to record multiple mics, especially when you deal with spatial information. But they might not necessarily be available, although we do have a few robotic systems now in our lab that actually allow us to do that. I think the really interesting question, though, would be, why do we constrain ourselves to two ears? Why don't we actually put microphones along the embodiment of the robot? And fundamentally, I think what that does is the robot moves, and as it moves, it fundamentally changes this geometry. But as a human listener, as we move, that actually tells us a lot about the acoustic scene. So if we can do that on a much bigger scale with many, many more microphones, I think there's a really exciting research question there about what would a machine perceive and how much sense could this machine make of an environment if it were being provided with all of this information from all these microphones that might be dotted over its body.
Yeah, that would be cool. I guess, you know, the challenge there as well is as the robot moves, it makes noises. So then it also has to learn how to recognize the noises it's making and sort of ignore those.
Yes, absolutely. So ego noise is a big and very specific problem that we have in robotics, actually. And again, a really interesting problem that we experience is that as a robot ages and gets used, obviously there's wear and tear. So what you recorded at the beginning of unboxing your robot, the noises that it might make at particular joints, for example, that might not be exactly the same footprint that it has a few years later as the robot has sort of been exploring the world and its parts have been subject to wear and tear. So again, there's a sense of dynamics involved, a sense of uncertainty involved that we need to incorporate when we actually handle and address these problems.
Yeah. So you also, you were talking about machine learning and, the large language models, the sort of the chatbots that everyone is now using. They were able to scrape a huge amount of written data off the internet, and that was very easy in a sense. By comparison, I mean, how much audio data is there available? Obviously, there's lots of videos on the internet, there's podcasts, but those have all kind of been tidied up a bit and edited, and a lot of the background noise has been kind of removed or dampened. How much kind of useful audio data is there available out there?
Yeah, that's a really interesting question. In terms of sound events like speech and music, I would say that there are a lot of very valuable data sets out there by now that are widely used within the machine listening community for training neural networks. The specific constraint that we have within robotics research is, of course, that machines move, robots move like humans do. And robots generally need to have a spatial awareness of the environment around them. Where is a sound source? If I want to interact with a sound source, I need to be able to know how to approach that sound source and how to physically interact with my environment. So robots have to have a lot of information about what is going on around them. In order to do that and train models to actually make sense of these very dynamic scenes where the robot might be moving, but also the human might be moving or other sound events might be moving, that requires us to actually have annotations of where each of these sound sources is actually located in space. And getting access to that kind of data is very difficult. So what I guess people are generally doing is to rely a lot on simulation. There are simulators out there that allow us to emulate how a sound wave would propagate in an environment and how a robot with a specific geometry of the microphones would actually perceive that sound field as it moves in the environment.
Okay. See, I was just thinking, like, just take the robot to a bar with you and train it on all of that sound that's going on around you. But that's not a very scientific solution.
I guess that's ultimately the aim, that we could deploy a robot in a realistic scene. There are, of course, also other considerations to make when we do that. So if you go to a public space and you record in a public space, in order to make sure that we're actually conducting responsible and ethical research, we need to make sure that the people who are being recorded have given consent and have given informed consent. So as such, it becomes reasonably tricky to actually record in public spaces. What we do here in Southampton is we've got labs where we can record and emulate rooms in controlled environments. So, for example, we have a new robotics arena, which is a 6 by 10 meter laboratory environment. And that will be equipped with a motion capture system. So a motion capture system allows us to track millimeter precise where objects within the environment actually are. And with that system, we can then allow a robot to basically roam in the environment, explore the environment, but fundamentally we have the ground truth about the positions of the robot as well as sound sources in that environment.
Yeah, that's really cool. You're currently leading a project on active audition for robots. So can you kind of explain what active audition is and how you're integrating this into robotics?
Yeah, of course. Active audition is about giving robots the ability to hear, but to hear with intent or to listen with intent. Humans do this naturally. So if we're in a noisy room, we turn our head, we lean forward, we nudge our head, and that gives us a more diverse perspective of the room and allows us to fundamentally work out how far a sound source is, what angle a sound source may be located at, for example. So physical movement for human listeners is actually part of how we perceive. The way that robot hearing works at the moment, or often works, is slightly different. So classically, it is assumed that a robot is a passive listener, or that the robot moves in a stop-start fashion, where effectively moves a little bit to achieve a certain aim, and then it stops to record. And then it moves again a little bit, and then it stops to record. And of course, that discontinuity is not very natural in how a machine would actually learn if it were to move freely within the environment.
Yeah.
But the reason that that is often assumed is that the motion of a robot actually destabilizes the hearing system. So fundamentally, the displacement of the microphone as the machine moves results in a shift in the robot's internal coordinate system and its mental map of the acoustic scene. So imagine you're looking straight and there's a sound source to your right-hand side. If you now rotate your head to the left-hand side, then of course the relative angle between your ears and that sound source also changes. And that change in reference frame becomes quite tricky to handle. With active audition, what we want to do is to give the robot the ability to actually move its senses or even reposition itself during listening. So effectively, we're trying to allow the robot to move in a way similar to humans and shape what the robot actually hears. And the key idea here is that when the robot moves, the sound around it also changes, and those changes actually help the robot to understand the world better. So as the microphones shift positions, the sound they pick up actually varies ever so slightly between different moments along time. And those tiny differences provide the robot with very important and rich information about the acoustic scene. For example, that the robot requires to classify what environment it is in, or to actually map where itself is located and where sound sources relative to it itself are located. So basically, active audition lets hearing drive action, I guess, and then the action shapes hearing. So it's simple for humans, but I think it's a big shift in robotics.
Yeah. It's funny to me how many things that we do without even thinking about it, just unconsciously doing these things, are really challenging for robots.
Absolutely. And I think that's really surprising for people, the general public, and researchers to actually discover as you go along about how many challenges are there that we just take for granted, that there's a system, our brain, that can solve these. And it actually really makes you appreciate how powerful and efficient our brain actually is.
Yeah, absolutely. I mean, one thing that strikes me is like, I don't experience each of my senses separately, right? Like, so my vision and my hearing and my sense of smell are all kind of combined into like a model of the world around me in my brain. Are robots able to do that? Or are they very much like having an audio experience and then a separate visual experience?
There's a lot of work on audiovisual sensor fusion, I guess, or on audiovisual processing. I think the ultimate aim is what we want to achieve is that the entire sensor suite that a robot has, so that's audio, vision, LiDARs, any other sensors, haptic sensors as well, could ultimately be integrated into one, I guess, holistic, unified system. That's sort of the really long-term vision and where I think a lot of researchers are probably steering. The key challenge for audio is that audio hasn't really received a lot of attention in the robotics community in a long time because it is such a difficult modality to deal with. And in my opinion, in order to actually now create something that is truly multimodal, so that can handle these different sensing modalities, we really need robust audio models and efficient audio models that allow us to do that.
Yeah. So, I mean, you mentioned earlier an important aspect of your work is kind of developing robots that are both sustainable and trustworthy. And sustainable in the sense that they don't rely on massive energy-hungry machine learning algorithms, and trustworthy in the sense that they are inherently interpretable. So can you tell us a little bit more about these aspects of your research?
Yes, of course. So modern AI often relies on huge energy-hungry models that are trained on vast data sets. That's fine when we actually operate in the cloud, but robots have very limited power and compute, and they need to make decisions in near real time or in real time. So a big part of my work actually focuses on making robot intelligence far more sustainable, both ecologically and computationally. So we want to develop algorithms and models that are efficient, but also interpretable. We do that by basically building much more structure and domain knowledge directly into these models that are driven by machine learning.
Okay.
So instead of learning everything from scratch, just by basically taking a generic architecture and giving it vast data sets, we want to build models that embed and translate knowledge that we have about the human auditory process, but also about the geometry of our robotic system and the way that the human brain extracts information, I guess, in acoustic scenes. Now, if the model starts with the right bias, the hypothesis is that it doesn't need millions of parameters or massive training runs. And that effectively makes the model smaller, faster, and also more energy efficient, which is exactly what we need for robotic systems. Also, these models, by embedding knowledge that we have about the human auditory system or mammalian auditory systems, is that it makes the model inherently interpretable, which then ties into trust. If we can interpret the model's decisions, there is a bigger confidence, I guess, in the model making the right decisions and a better understanding of when the model doesn't make the right decisions. So if a robot is making decisions in the world, we need to understand why it may or may not be making wrong decisions at times so that we can actually address that and correct it. And fundamentally co-design with the public systems that are useful for society. And I believe that structured models help with that. So we can trace back decisions to meaningful cues. So for example, how a robot perceives different spectral cues, so frequency cues, like the pitch of your voice or the modulation of your voice, rather than just providing you with opaque internal representations that are really difficult to actually understand from a human perspective. So by building models that are lean and structured and grounded in real perceptual principles, we are building robots that make better use of their resources, that are easier to adapt, and whose behaviors we can actually understand.
So these structured models are basically like giving it a cheat sheet of here's what to pay attention to, here's what to look out for, this is what's important. before it starts kind of being trained on the data?
So basically, the human hearing process can be modeled as a cascade of filters. So a filter is effectively a mathematical operation that extracts or modified features that are embedded in the signal and the signals that are picked up by the robot by its microphones.
Okay.
What we do is to explicitly design the general structure of these filters, how the filters are connected together to perform some function that we roughly believe happens at a certain stage throughout the hearing process. So think about, for example, the human cochlea progressively analyzes sound and breaks it up into different frequency bands and temporal patterns. So fundamentally, if we can design a structure of filters that allows us to create these sort of maps, then the open question still remains exactly what response do these filters have to have. So we have the rough sequence of there's a filter that breaks it down into frequency patterns, and perhaps another filter that then has a context window and looks over long and short context windows, what's happening in a signal. Once we have that structure in place, we now need to learn exactly what filters are required to make sense of the signal in order to solve a particular listening task. And that's then where deep learning comes in. So provided with this general structure, deep learning now allows us to learn the precise filter shapes and parameters by basically exposing the model to lots of different audio examples in datasets.
Yeah, that makes sense. Thank you for explaining it so clearly.
Thank you.
Christine, it's been great chatting to you today. I've been talking to Christine Evers from the University of Southampton. Thank you.
Thank you very much for having me, Claire. It's been a pleasure being here.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. And if you've got a question you'd like me to ask one of my future guests, you can contact me on social media at Robot Talk Pod, on Patreon at patreon.com/Claire Asher, or at robottalk.org. I regularly announce upcoming guests on all those platforms, and I'd love to include your questions in my next interview. Next week, I'm chatting to Amir Patel from University College London about robot balance and agility. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.